The goal of the project was to improve the storage of energy from solar panels. This was accomplished by designing the most energy efficient and cost-effective pump storage facility. Seymour Crystals consulted Team 17 to create the most effective pump storage facility. Solar energy is at the forefront of innovation, and improving the storage of the energy captured by solar panels will allow for a quicker transition to renewable energy. It is necessary to create an effective storage facility, since solar panels can only collect energy during daylight hours. By converting the energy to gravitational potential energy, it can be accessed at any time, not just when the sun is out. In order to accomplish this, it was necessary to choose the best site to construct the facility and the parts for optimal efficiency.
Team 17 developed a Gantt chart to keep track of the development of the system, with time periods for research, determining the factors as well as the equations, developing the code, and testing the code. Once the code is developed, the next step is to test it and to find the best system. And in order to choose which site the facility would be built on, a decision matrix was developed with criterion to aid in the choice of the site. The scores were based on the amount of usable space, the angle from the river to the plateau, the elevation, the horizontal distance from the river, the cost of the access road, the site preparation costs, and any other additional costs. Zone 1 had the most usable space, the lowest angle of elevation, smallest horizontal length, lowest access road cost, and the lowest area preparation cost. All of these factors led to the decision to develop the site on Zone 1. Various factors were considered for the model: the expansion of the pipes due to heat and the effect of local fauna drinking water. Both of these factors were considered to be insignificant. The animals drinking water was able to be circumvented by building a high enough wall to keep the animals out. The expansion of the smallest diameter pipe available expanded only very slightly at high speed of water for a 5 degrees Celsius temperature change. A model was developed to calculate the input energy and the efficiency of the system. In order to test the model, various inputs needed to be tested to determine what would be the most efficient system and the least costly system. Many of the inputs were kept constant to reduce the number of choices made. For example, the system should use the full 12 hours to pump the water up and the other 12 to bring it down. The height of the system was kept constant at 5.1 meters tall, and the length of the pipe was kept constant as well.
So as Team 17 discussed in the methods section, the tests were run with varying values for the different inputs. The volumetric flow rates were left constant to ensure that the empty and fill times stayed under the 12-hour limit. By making the time exactly 12 hours, volumetric flow rate was the lowest that it could be. Because of this, the water velocity and therefore energy losses to pipe friction and pipe bends were decreased. Testing started for the most energy efficient solution by choosing the best possible options from the parts catalog. Then testing began for the most cost-effective solution by choosing the cheapest materials in each category. This helped establish an upper and lower bound for the efficiencies and prices. Next, a series of intermediate values were tested. However, a trend became apparent early on. As shown in the results section with the maximum and minimum values, as the price slightly decreases, the efficiency essentially tanks and the worth of the system is diminished. Based on various tests, Team 17 noticed that the smallest changes to decrease cost hurt efficiency greatly. This can be seen by the horrible efficiency value for the cheapest model, which is roughly 1,000,000 times worse than that of the most efficient. Based on this, we came to the decision that cost was not as important as efficiency, and therefore chose the solution of maximum efficiency, previously labeled as the upper bound. This gave an efficiency of 0.83 and a minimal input energy of 144.89 megawatt hours. As seen in Figure 3 showing all calculations, the final price including site and build costs was totaled to $467,293.68.
We used a Python program to demonstrate our model, and we calculated the total energy into the system along with the time it takes to move the water from the river to the reservoir, along with the time it takes to move water from the reservoir to the river, and finally the efficiency of the system. And the program focuses on the energy efficiency rather than the cost. We calculated the cost separately, and we organized our program by functions, variables, the actual calculations stored in the variables, and then the outputs. So first we calculate the pipe area, which is simply just pi r squared. We take in the pipe diameter divided by 2 and then plug it into r squared. And then for the reservoir volume, we calculate the volume simply just by multiplying the area times the depth. And then for the reservoir mass, we multiply the water density times the reservoir volume. And then we move on to the velocities. We calculate the up velocity and the down velocity. And we do this using the calc velocity function, which divides the flow volume divided by the area to get each respective linear velocity. And then finally we calculate the energy loss from each pipe bend. So we did it for going up and down for each bend using the calc E bend function. So using the calc E bend function, we multiply the mass of the water times the pipe loss coefficient times the velocity squared divided by 2. And then we add up all these bent energies up for later calculations. Then we calculate the turbine energy loss using the turbine energy loss function, just E out times the quantity 1 divided by the turbine efficiency minus 1. Then we calculate the friction loss going up and going down using the calc E friction function, and that just takes the mass times the pipe friction factor times the pipe length times the velocity squared divided by 2 times the pipe diameter. And then we calculate the En. We calculated it using the universal accounting equation. We did this separately on paper, and then we plugged it into the program. It's just the En is equal to E out plus the turbine loss plus the friction loss going up, the friction loss going down, plus the total energy loss from the bend divided by the pipe pump efficiency. And then we calculate the pump loss energy by taking in the pump efficiency and the En, which we calculated earlier, and then we do 1 minus the pump efficiency times the En, and we find this total efficiency simply by dividing E out divided by En. Then we calculate the time it takes to move the water up by simply dividing the reservoir volume by the pump flow volume and then converting it to hours, then doing it for the time going down as well. Then we convert joules to MWH. For En, we output the zone 1 reservoir area, we output the En and MWH, then we calculate the total efficiency, the time it takes to go up and the time it takes to go down. So demonstrating the program using the values we entered. We get a En of 144.89, we get a efficiency of 0.828, then we get a time to fill and a time to empty of about.
This solution provides the optimal efficiency at a reasonable cost. With an efficiency of 0.828, the pump storage facility can convert energy gathered from solar panels to gravitational potential energy and store for as long as needed. This solution increases the usefulness of renewable energy and allows those sources to have a larger role in society. The 12-hour fill time and 12-hour empty time allow the facility to pump water to store for energy during a 12-hour period of daylight. Then, it can release energy for the full 12 hours of night if needed to support people's energy needs while the sun is down. This feature overcomes one of the largest problems with solar energy, as it is now accessible even when the sun is down. In the long run, this technology will make it easier for society to be more reliant on renewable energy. This will aid in stopping climate change, thereby protecting the environment.